Welcome to lesson 10-7, special segments in a circle. All right, this is the most surprising theorem in the whole book to me. It's a shame we're not together to celebrate it. If we had been, I would have started class with a big circle on the board and asked somebody to just call stop 4 times as I moved my marker around the circle and just get 4 points, make 2 segments that intersect. These are actual lengths here. I don't know how well you'll be able to see from your monitor, but this really is 2 centimeters like it says. This piece really is 14 centimeters like it says. And over here, this really is 4 centimeters. Maybe you can see it, maybe you can't, but you could try this at home. And this piece really is 7 centimeters long. So these are real measurements. Notice they are not perpendicular to each other. They're not congruent to each other. This is a length of 11. This is a length of 16. They're not neither one's being bisected. It's literally any 2 segments that intersect. That's the only requirement in a circle. Any 2 chords in a circle that intersect. And isn't it amazing? Look at those numbers. Does that blow your mind? What's 14 times 2? 28. What's 4 times 7? Why does that work? Why did the product of those pieces come out to equal the product of those pieces? Did one more on the back. Total length of 17 is cut into 8 and 9. Total length of 18 cut into 12 and 6. This really is, I won't measure them all, but I'm sure you trust me. This really is 6. This really is 9. These are real measurements. 12 times 6 is 72. 8 times 9 is 72. I don't even know what it means to be multiplying pieces of a chord together. I know what it means to add them. It tells me how long the whole chord is, but 12 times 6, what does that mean? I don't know, but I do know it equals 8 times 9. So why does that happen? Let's look at this picture. So I'm claiming A times B has to equal C times D. You might want to pause it yourself, see if you can figure out why that's true before I give it away. Here we go. I'm going to add couple of segments. Bow tie theorem, anyone? Bow tie theorem from earlier in the chapter tells us these angles have to be congruent because they have a vertex on the circle. Each one is half of that arc. These angles have to be congruent from the bow tie theorem. Vertex on the circle, each one is half of this arc. And of course, vertical angles are congruent always. So tell me something about those triangles. Correct, they are similar. AA similarity. So we can write proportions. A side of this triangle is A. Corresponding side of the other triangle, based on the angle markings, would be the, would be the D, right? A is between double, triple. D is between double, triple. So there's one ratio of corresponding parts, and since the triangles are similar, it's going to equal another ratio of corresponding parts. C from the big one, single, triple, is going to correspond to the B. So this has to be true because we have similar triangles. And if that's true, whatever we get when we cross multiply has to be true. Cross multiply, what are we forced to admit? This times this must equal this times this. AB equals CD. Unbelievable. So down here, pause it for yourself. Figure out what X equals. I'll give you a hint. You don't have to draw the extra chords. Just use the theorem that we just proved. All right. Hopefully everybody for a simple equation. 2 intersecting chords. This piece times that piece must equal this piece times that piece. Divide both sides by 4. X is 10.5. Just like that. So that works for any circle all the time. So even if you have this big circle, a long chord and a short chord, it still works. This length times this one will equal this one times that one. I just find that amazing, even though I just proved to you why it works. So here's the other thing we need to look at. How about two secant segments? So secants, they hit the circle twice and they intersect outside the circle, as opposed to the previous one where they intersected inside the circle. There is also a relationship between these four lengths. This one's a little bit messier than that first one, but I'll do my best to try to, and I don't even know if this is going to work well on video. Excuse me, I'm changing my mind. I'll give you a hint if anybody wants to try to figure this out. By adding these, there's a bow tie here, and the bow tie theorem tells me that this angle is congruent to this angle. The triangles I'm looking at are this big triangle, I'll call it triangle QRS, and I'm looking at this big triangle. QMT. So they're overlapping triangles, sort of hard to spot. But because they share this angle, which is congruent to itself, these triangles are similar from AA similarity. Both triangles have a single marked angle and a double marked angle. So that means that triangle SQR must be similar to triangle TQM. And maybe I'll leave a little bit of the work for you if you want to play around with this. It's very similar to the last example I did. Because of these similar triangles, there is a proportion you can write. A side of this triangle over a side, the corresponding side of the other one, equal to another side of this one over a side of that one. And if you cross multiply, what you wind up getting, so a little bit of a cliffhanger for you to play around with, but the end result, what you should be able to prove from there, is that on this picture, which was the original picture, here's what you'd get when you cross multiplied. The piece on the outside of the circle, A, times the entire secant length, which is A plus B, is going to equal, from the other segment, the part on the outside C times the entire secant segment, which is C plus D. C plus D. So I'm going to say that again, because this honestly is how I think about it in my head. They have to be secants. They have to each hit the circle twice. And what you can prove from these similar triangles is the part on the outside times the whole thing equals the part on the outside times the whole thing. That's how I say it in my head. Outside times the whole thing equals outside times the whole thing. So it even works if one of them is a tangent and the other one is a secant, and they meet outside the circle. It still works out to be the case the part on the outside times the whole thing will equal the part on the outside times the whole thing. Well, C is the part on the outside and C is the whole thing. So that just means C times C, C squared. So this is another theorem. A tangent and a secant meeting outside the circle. Part on the outside times the whole thing equals the part on the outside times the whole thing. And if you want to try to prove that to yourself, I'll give you a little hint. You may have to draw one or two extra convenient segments in this picture. Maybe from here to here, maybe from here to here, maybe both. But there are some similar triangles you can use and get this relationship. So a couple of examples. If I want to get x on this picture, why don't you pause, see if you can come up with the correct equation. I'll give you a moment. So what you should have had was this for your original equation. 3 is the part on the outside. The whole secant length is 3 plus 10, so 13. So 3 times 13, not 3 times 10, 3 times 13, it's the whole length, equals 4 on the outside times 4 plus x, which is this whole length. So outside times the whole equals outside times the whole. And if you distribute the 4 and go through your algebra, you wind up with 23/4 or 5.75. Last example for today. One more problem you can try on your own. Hit pause when you've got a good look at it. All right, so we've got a tangent and a secant meeting on the outside. So we know the part on the outside, 5, times the whole length, which is 5 plus 9, is equal to the part on the outside, x, times the whole length, which is x. So x times x squared. So 14 times 5 is 70. That's x squared. So to get x, we're just going to square root both sides. We know it can't be negative, so we only need the positive answer. Answer is the square root of 70, which cannot be simplified. So that's it. That's the answer. I think you'll be fine if you watch this video a couple times. Hope you found that helpful. Bye-bye.